Hello everyone. In this video, we're going to look at the IPv4 packet format, discuss IP packet fragmentation, and briefly examine IPv4 addressing. In its most basic sense, the network layer is responsible for packet forwarding, including routing packets through different networks. To perform this function, the routers compute path selection with routing protocols such as OSPF and BGP, which we'll study in Chapter 5 next week. In order to identify each host and router on the network uniquely, the network layer defines an addressing scheme. The network layer also defines specific methods of dealing with the packets. Error reporting and ensuring a certain quality of service also fall within the purview of the network layer. The IPv4 packet format is depicted on this slide. The first field defines the IP protocol version, which in this case will be IPv4. Next, there is the field, header length, which gives the length of the IP header in bytes. This field is necessary because the IP packet format allows for an option field, which makes the field length vary. The type of service field, TOS field, the second byte of the IPv4 header, has been renamed to the differentiated services field. With the advent of real-time services such as voice over IP and streaming video on the internet, this field has become more important. This field is actually divided into two subfields, which are 1. Used to classify traffic and set packet priority for quality of service, and 2. Aid traffic congestion control. The length field contains the total number of bytes in the IP packet. We will discuss the fields in the second row in the two slides following this IP packet slide. But first, let's look at the remaining rows. The time to live field, or TTL, shows the remaining number of hops through the routers. The TTL is set at the source host and is decremented each time the packet passes through a router. If the TTL reaches 0, the packet will be discarded. Although the 8 bytes in this field allow the TTL to be set at 255, in practice, different operating systems use different default TTLs. The Mac OS and later versions of Linux use a default of 64. Windows uses the value of 128. Early versions of Linux use a maximum of 255. The purpose of the TTL field is to prevent a packet from being routed forever because of routing loops. The next field, the upper layer field, indicates which other layer protocol is being used. We would typically expect this to be the transport layer, either TCP or UDP. But an example of another upper layer protocol would be OSPF, a routing protocol that's really at the network layer. The 16-bit IPv4 header checksum field is used for error checking of the header. When a packet arrives at the router calculates the checksum of the header and compares it to the checksum field. If the values do not match, the router discards the packet. Both the source and destination addresses are 32 bits long. This allows for approximately 4.3 billion unique addresses. The options field is used for testing, debugging, and very limited security. It is used infrequently. The last field of the IP packet includes the useful application payload data plus the upper layer headers. We will talk about the ID field and the two other fields, the flags and offset fields, in the following two slides. How much of this header is overhead? The answer is 40 bytes, with 20 bytes for TCP and 20 bytes for the IP header. Note there is also overhead in the application layer. The amount of this overhead is dependent upon the application. Now we can discuss the second row of the IP packet format. The fields here are used to facilitate IP packet fragmentation and reassembly. All network links have a maximum amount of layer 3 data that can be transferred in one layer 2 frame. This is called a maximum transfer unit, or MTU. Data link layer technologies can vary across networks, which means that their frame size limitations can be different. For example, the largest standard Ethernet frame is 1,518 bytes, which includes the Ethernet overhead of 18 bytes. So the MTU for Ethernet is 1,500 bytes. But IP packets can be larger than the largest possible link layer frame. Now, what happens when a large IP packet crosses over or arrives at a network where the packet is much larger than the MTU? The packet gets split into multiple packets. This is called fragmentation. In this diagram, a host creates an IP packet and sends it to its edge router, which then forwards it to another router. Because the network links on this path so far, supporting an MTU that is large enough to accommodate the size of the packet, the entire packet is transmitted. But now the packet is sent to the next router over a different link type, which has a smaller MTU. So now the packet must be split into smaller packets. This process is called fragmentation. These smaller packets then traverse the rest of the network path and get reassembled at the receiving host. Note that fragmentation can occur in the middle of the network. Reassembly, however, does not occur in the middle of the network. Reassembly only takes place at the final destination. There are 3 fields used for fragmentation: ID, fragment flag, and fragment offset. The ID field is 1 byte number that identifies this specific packet. This field will be used to identify all the fragments of the original packet so they can be put together. The flag field indicates whether or not the original packet has been fragmented. The fragmentation offset value points to where the packet has been split. Let's look at an example of IP fragmentation and reassembly. In this diagram, an IP packet of length 4,000 bytes is sent out by the host. On the slide, the ID is just labeled X, where the X could have any of approximately 65,000 values. Initially, the fragment flag and the offset are set to 0 because the packet has not yet been fragmented. The packet is sent to the first router, which forwards it to the second router intact. The output port of the second router is connected to a network whose link layer protocol has an MTU of 1,500 bytes. Here, the second router must fragment the larger packet into 3 smaller packets. We see that the first fragment's length has been shortened to 1,500 bytes, which includes 1,480 bytes of data plus the IP overhead of 20 bytes. The frag flag has been set to 1, but the offset is 0 because this is the first fragment. The second fragment is also 1,500 bytes long, with the frag flag also set to 1. Now the fragment offset value is the size of the data portion of the fragment of the preceding fragment in multiples of 8 bytes. In this case, the data portion of the second fragment starts 1,480 bytes into the original IP datagram. So you get 1,480 divided by 8 equals 185. The third fragment's length is 1,040 bytes. This is the remaining data portion of the fragment, plus 40 bytes for IP packet overhead of the second and third fragments. The offset value is now 370, which is the size of the data portion and all the preceding fragments expressed in multiples of 8 bytes. Since there are no more fragments, the frag flag has been cleared. Now, using the information in these fragmentation fields, the receiving host can reassemble the IP packets, even if the packets are received out of order. We will now look in more detail at IP addressing. Hosts are physically and logically connected to networks at the interfaces. Some hosts have single interfaces or multiple interfaces. Routers will always have many. These interfaces have link layer elements that connect them to the local network. We will talk more about the link layer in Chapter 6. To communicate beyond the local network and on the Internet, each of these interfaces must be assigned an IP address. In the network diagram, we see groups of hosts connected to the router at 3 interfaces. As we discussed, the IPv4 addresses are 32 bits long. At the bottom of the network diagram, an IP address for one of the hosts is listed in 2 ways. One notation is as a string of 32 bits. The other is the common notation that we're all familiar with, 4 decimal numbers separated by a period. In this case, 223.1.3.1. This familiar representation of an IP address is called the dotted decimal notation. In this notation, the 32-bit address is divided into 4 bytes, and each byte is converted into a decimal number. The 32-bit address contains 2 parts. The high-order bits, or leftmost bits, define the local network that the host is connected to. The low-order bits, or what remains, are what can be assigned to the host interface. The network portion is called the subnet. Devices or hosts that are on the same subnet can communicate with each other without using a router. They use the link layer, or layer 2, to communicate. The subnet mask is what tells you where to divide the IP addresses into the network part and the host part. The bits defining the network part of the mask are always 1s, and the bits in the host part are 0s. The subnet mask is usually written as a slash followed by a number of network bits in decimal form. As an example, /24 indicates 24 bits are used for the subnet mask. Originally, the allocation of IP address space was divided into 5 classes. Classes A, B, and C were distinguished by the byte boundaries. Class A used the first byte for the network and 24 bits for the host, which made for 127 very large networks. Class B network eventually divide the network, the host, and the network parts into 16 bits each, 65,000 possible networks with 65,000 possible hosts. Class C networks had 24 bits designated the network number and 8 bits for the host. The other 2 classes had different purposes. This subdivision of IPv4 address space was very inefficient. The IPv4 classes have now been superseded by classless interdomain routing, also called CIDR, C-I-D-R. With CIDR, the subnet portion now can have an arbitrary length. This diagram shows 3 subnets that are connected to the separate interfaces on the router. Observe that each subnet has a mask of /24, which is a shorthand for the 24 1 bits in the mask as shown in the parentheses at the lower right-hand part of the slide. By performing a binary AND operation with the IP address and the subnet mask, we can determine the network number of each subnet. As shown on the diagram, the 3 networks are 223.1.1.0, 223.1.2.0, and 223.1.3.0. With the /24 network, there are 8 bits used for the host addresses. That many bits mean there are 256 possible host addresses. That's 2 to the 8th power. In each network, 2 of the host addresses have special purposes and can't be used for the host interfaces. The first possible address of the subnet defines the network, and the last possible address is the broadcast address. which is the address the host uses when it wants to communicate with all devices on its local network. So each subnet in this diagram can have 254 hosts. This next diagram shows a new network design with the same host subnets, but now with 3 routers. How many subnets are there now? Notice that in addition to the subnet with hosts, there are 3 point-to-point links just connecting the routers. These links are also subnets. So in this diagram, there are 6 subnets. To accommodate 2 hosts, you could use the subnet mask of /30 using the rule that 2 addresses in each subnet cannot be used. The leftmost link connecting the routers is probably using this mask. Since point-to-point links do not require broadcast, though, they're only communicating with one other host, in this is a special case, we could use a /31 network. The other 2 point-to-point links would probably be designed to have that mask. In the next video, we'll continue our discussion of implementing IP addresses.